Hi everyone. Good to see you. So this is going to be the review session for your final. Final is going to be on Friday. So let's talk more about the details about our final party. Okay. So all right, so we have a final scheduled on Friday. Our final party, right? It's Friday, May 1st from 7 to 9 a.m. Okay, so we have 2 hours for the final exam, and then like the midterm number 2 that we had a couple weeks ago, I'm going to provide 15 more minutes at the end to upload your work, and that work should be in one PDF file. So exactly the same thing. You have to take your work in a picture, and then using the whatever app you use, just convert and combine it into one PDF file so that you can upload it on the Blackboard. So the Blackboard test will be available from 7 through 9:15. Okay. Okay, so you have a full 2-hour time period for solving the exam, and then at the end you have 15 minutes to convert your work into one PDF and upload it on the Blackboard. And this final exam is comprehensive, which means it covers everything that we learned during the semester. So we had chapter 1, chapter 2, chapter 3, 4, 5, 6, and then 8, 9, 11, 12, and 14, and 16. So I'm gonna briefly go over every chapter today, especially chapter 4, 5, 6 were covered in midterm number 2, and we already have a review session for that. So I'd like to refer the other video clip, which is still available on the Blackboard and the YouTube as well. This is for review for midterm number 2. And we already covered chapter 1 through number 3 in midterm number 1, but we do not have a video clip for that. So I'm going to briefly touch those 3 chapters and then later chapters as well. Okay, so in chapter 1 and 2, actually it was kind of an intro to steel design. So we talk about the basic concept between analysis and design, what we have to learn about design steel members, right? So basically we're satisfying this equation, capacity larger than or equal to demand, and we have 2 different methodologies available in this class and available in this steel design. One is LRFD and then ASD. So in chapter 2 especially, we talk about how we can calculate the demand and how we can apply the factor of safety, because we have 2 different methodologies in 2 different ways. For example, LRFD, we use P factor to take account for uncertainties. ASD, we have omega factor, and these P factor and omega factor, those are all for capacity side. ASD doesn't have any additional factor for demand calculation, but we do have the demand factor, the load factors for LRFD. So that's one of the main difference between LRFD and ASD. And the difference between LRFD and ASD is quite important. So that's why we had a reading material, then there is one reading assignment for that. So that would be one good topic to cover these two chapters. We also talk about the material properties. We also talk about the load factors. I already mentioned that. So those are the first two chapters in this class. And by the way, we have two different type of problems for this final. We do have calculation type problems, of course, because this is a design course, but we also would have the problems asking the concepts, right? Like I mentioned, what is the main difference between LRFD and ASD? That would be the good topic. We also talk about very specific concepts and definitions, and for example, the failing mechanism. What is the main failing mechanism for the bending members? That's a lateral torsional buckling. Or we also talk about the effective length and effective length factor for a compression member. We also talk about different failing mechanisms for tension members like yielding, rupture, and block shear. We also cover chapter 12 and 14. For example, these are the connections. We have a bolted connections and welded connections. We did not go over any calculations for those two chapters, but we cover some concepts and some different methodologies. So those are the topics that you have to prepare for this final exam. Okay, chapter 3 and 4, this is for tension members. Chapter 3 is analysis of tension member. Chapter 4 was design of tension members. Chapter 5 and 6 were for compression members. Chapter 8 and 9, this is for flexure members, which is the beams. Chapter 11 was for beam column. Chapter 12 and 14, connections, bolted connection and the welded connection. Chapter 16 was for composite members. Okay. So again, chapter 4, 5, and 6, we already I already went through the review session for midterm number 2, and that video clip is still available, so you can watch that video clip again to cover these 3 chapters. So I already mentioned the chapter 1 and 2. Chapter 3, the analysis of tension member. So tension member, we studied it as the very first type of the member, because the tension and compression both are axial load. Axial load is the basic and the simplest type of load, and tension is simpler than compression, because compression we have always a very unique failing mechanism, which is the buckling failure, but tension does not have that buckling as a problem. So the very first chapter, chapter 3, we get into the real design problems. We talk about the failing mechanism, which is the limit states, and the limit states for tension member typically yielding and rupture. Some special conditions, if we have a series of bolted connections or welded connections, and we can have a block shear as a special failing mechanism. So it's kind of optional, but the yielding and rupture are always there to determine which one is going to be the governing or the more critical limit state, the failing mechanisms for the tension member. Yielding limit state, this is the nominal equation. Pn is equal to Fy times Ag the rupture limit state Pn is equal to Fu times Ae, right? So Fy, Fu, those are the mature properties. For A992 steel, for example, Fy is 50, Fu is 65. So it is depending on the mature properties. And Ag, that's a gross area. Ae is U times An, and An is the net area. So the rupture limit state is along the line with the hole, because when we have a bolted connection, we have to make a hole to, that bolt can go through. And because of that reduction of the area, we will have a minimum kind of a deducted area in that portion, right? So you have to identify the size of the hole, which is usually 1/8 inch larger than the size of the bolt. And then when you deduct the area of the hole, that will be the area, net area An. This U is a shear lag factor. So shear lag factor, we have several different ways using when you go to the table. The table listed a total of 8 different cases, and depending on the style of your section, like the W shape or the L shape, or depending on the different shape, you have a different cases. And very typical equation for the U factor is this. So 1 minus x bar over L. X bar is the distance from the centroid of your section to the edge of the surface that you have a connection, and L is a connection length. So there are several different example problems to go over those things. And the practice example problems would be example 3-1 through 3-6. So these all 6 example problems, I believe we went over all the problems in the class, and these are going to be the good the practice problems. And 3-12, this is for block shear failure. Okay, and 3-1 through 3-6 will cover both yielding limit state, rupture limit state, how we calculate and estimate the net area or shear lag factor, effective length at the effective area. We also talk about the staggered pattern and how we can calculate and identify the gauge lengths and the pitch, and to estimate the net area correctly. So these are the practice problems for chapter 3. Okay, so I'm going to move on to chapter 8 and 9. So chapter 8 and 9, this is again the analysis and design of flexure members. So chapter 8 is analysis. Chapter 9 is for design of flexure members, which is beams. And this is very similar to the chart we use in chapter 5 and 6 for the columns. But basically, this is the basic fundamental for the beam analysis and beam design. So we have total of 3 different regions to calculate the nominal moment capacity. And for the beam analysis and beam design, in chapter 8, by the way, we talk about, before we get into the equations and this chart for the beam analysis and beam design, we talk about the section modulus. S is an elastic section modulus, which can be calculated as I over C. And we also talk about the Z. This is the plastic section modulus. Okay, and we use this Z value to calculate the very top and the maximum nominal moment. So this chart is talking about the nominal moment over the unsupported length. So this L sub B is called unsupported or unbraced length, depending on how many and how often we have a lateral support, we can identify this unsupported length, right? Okay, so that L sub B versus M sub N, the nominal moment, which is the kind of calculated moment for the beam, and the relationship between these two quantity is the main chart for understanding the behavior of the beams. And we have so we have total of 3 different reasons. Reason number 1 is the case when L sub B is less than L sub P, that we call the fully plastic moment. So this is the case when M sub N is equal to M sub P, and M sub P is simply Fy times Z, this plastic section modulus. And equation 8-1 is covering this plastic section modulus. And one of the problems in entertainment package number 7 also covering how to calculate the plastic section modulus. Basically, plastic section modulus can be calculated as the first moment of the area, and that is based on the plastic neutral axis. Plastic neutral axis is the line that will divide the entire area into 2 same areas, which may not be the same location as the elastic section the elastic neutral axis. The elastic neutral axis is passing through the centroid of the section, so that is based on the centroid calculation. And plastic neutral axis is purely based on the area. Anyway, so that's the first moment, M sub P, right? When L sub B is less than L sub P. Now, if L sub B is in between L sub P and L sub R, by the way, these two numbers, L sub P and L sub R, those are 2 unique values for each section. And in the table under the flexion member chapter, there is a calculated quantity for L sub P and L sub R. So bottom line is, when the section is given, you can go to the table. Those LP, LR values are already given. So you can compare your unsupported length to L sub P first. If L sub B is less than L sub P, then your nominal capacity is going to be same as MP, which is Fy times Z. If your unsupported length is larger than L sub P but less than L sub R, then we have equation looks like Mn is equal to Cb times MP minus Mr. You remember this, right? LB minus LP, LR minus LP, right? So MP, which is Fy times Mz, and Mr, there's a specific equation for that. So when you look at this equation, let's talk about C sub B in a minute, but MP is kind of a, you can calculate it. It's not a function of L sub B. So in this equation, L sub B is the only variable. LP, LR, LP, those are all constant, and MP and MR can be calculated as well. So that's how we combine these two as BF. That's the one used in the manual, best friend, right? So for example, LRFD, we multiply by phi factor. So that's why the steel manual have phi times MP and phi times BF, so that when you multiply by phi, that phi goes here, and that is going to be multiplied by MP here, and BF, that covers everything here, right? So when you just substitute your whatever unsupported length here, and then subtract L sub P times phi times BF, and you subtract it from phi times MP, that is going to be your factored nominal moment. For ASD, of course, you're going to use a omega factor. So this is the equation when your L sub B is in between LP and LR, and that is called inelastic lateral torsional buckling. By the way, lateral torsional buckling is a feeling mechanism for the flexure members, the beams, right? If L sub B is larger than L sub R, then it is called elastic lateral torsional buckling range, and this is not a good way to utilize your section, right? Because you cannot have that much of capacity compared to the maximized capacity, which is M sub P. So this is the main concept which is used in both chapter 8 and 9, analysis and design of the beams. And you might remember that we use the chart, which is overlapped chart of these three curves, for all the sections available. So when you have unsupported length and then calculate the demand, find out the intersection point larger than, or on the right hand side, find out the first straight line, the bolded line, which will give us the lightest section, right? So that's how we use a chart to design the beams. And the good exercise practice problem would be example 9-1, 9-2, 9-6, and 9-8. By the way, all these problems and all these explanations are available. So after this review for midterm number 2, all the lectures are available in a separate video clip, right? So that's what I'm not covering all the details here again, because you already have available video clips for those. So these 4 problems would be a good the practice problems and the entertainment package number 7 as well. Okay, so those are the chapter 8 and 9. Save it. Let's go on to chapter 11, 12, and 14 and 16. So let's see, I'm going to raise this part. Chapter 12 and 14, because we already we went through only the concepts of the vaulted connections and the welded connection. I didn't go over any problems, the calculation type problems. So I do not expect you to have any calculations for those 2 chapters. Just review those, the PowerPoints, and that would be the good. You can prepare it well for those 2 chapters. Let's look at chapter 11. So chapter 11 is for beam columns. So the basic idea of the beam columns are the beam column, usually the compression member are not just standing alone. It is connected to other members, typically either slabs or the beams, right? And those are the members having the bending moments developed inside of the member due to the gravity load or the transverse load. And those bending moments are going to be eventually transferred through the compression member. So this column is not just a pure compression member at all. Many times, in most of the cases, these columns are working as a beam column, meaning we have a compression plus the end moments at the top and the bottom. So that's the main topic in chapter 11. For beam columns, this is the main equation. So first thing you have to do is you have to calculate the capacity and demand against the actual load, the actual compression. PR is the so either PU or PA, depending on the methodology. PU for LRFD, PA for ASD. So this is going to be the demand, and PC is going to be the capacity. So take the ratio between capacity and demand. If this is larger than or equal to 0.2 or less than 0.2, we have 2 different equations to calculate the whether our beam column is safe or not. So the equation looks like this: PR over PC plus 8/9 times MR x over MCX plus MRY over MCY. So if this value is larger or equal to 0.2, then you have to use this equation. If this value is less than or equal to 1.0, then you're okay. That means your beam column is safe to hold these compression and the bending moment. If PR to PC ratio is less than 0.2, then the corresponding equation is PR over 2PC plus, there's no 8/9, the ratio, the other things are the same, MCX plus MRY to MCY, the same idea. So if this ratio is less than 0.2, then you have to follow this equation. This value, if the quantity from this calculation is less than or equal to 1.0, then your beam column is safe. In other words, when you calculate the number in larger than 1.0, that means your column is not good. And we went through example problems 11-1 and 11-2. There's no entertainment package for beam columns, so these two problems are going to be the good practice problem to prepare this chapter 11. Again, chapter 12 and 14, no calculation problems, so just go over the PowerPoint. That should be good enough. And chapter 16 was the last chapter that we covered the composite members. So I talked about the concrete slab with the steel member, right? And since we didn't go over any entertainment package problems, so I'm going to give you the one problem from chapter 16 as an extra point problem, okay? So erase this portion. So the last video clip, the second one in week 15, covered the composite section, the chapter 16. And then I think that video clip would be good enough. And in that video clip, I went over the example 16-1. So when we have a concrete slab with a certain effective length, and then here we have a steel section underneath, and the section is given. So this is an analysis problem, not a design problem at all. So W whatever section, and then the effective length and the thickness of the slab, those are all given, and this is going to be D. And the first thing we have to do is that calculate small a value from Fy AS divided by 0.85 F prime C be effective. If this a value is larger than T or less than T, so less than or equal to or larger than T, so that will determine which case that we have to solve this kind of a problem. And example 16-1, in that example, we only cover the case C, I believe so, that this A value, A is, by the way, the width of the compression zone for the concrete, and that is less than or equal to T. Then we have a certain equations to find out the moment arm, and then using the equation, you can easily find out the factored moment capacity. So if you're confident to solve the example 16-1, that should be good enough. Okay, so I think this short video will cover the basic idea about the final exam. Again, it is going to be on Friday, early morning, 7 to 9 a.m. And then I'm going to give you the the extra 15 minutes to upload your work. One last thing, you might know that the Monday is going to be the last day for the teaching eval. So you probably received an email from the university about the teaching eval for this class. So if you already completed it, thank you very much. If you didn't or forgot to do that, please do so. So that's one thing. The other one, it is separate from the teaching eval by the university. This is for ABAP purpose. So there's a separate kind of a assessment thing, which is called the course outcome survey. Oops, outcome. Come on. Outcome survey. So you might remember that in our syllabus, we were at the first day of the class, I went through these are the goals for this class, and I'd like to meet these goals throughout the semester, and each goals are lined up with the outcome, the program outcome of the civil engineering degree. So I'm going to post this course outcome survey under week 16 folder. So you can find this final exam under week 16, and then you will see this course outcome survey as well under week 16. So please complete this course outcome survey as well. All right, so this is the last video for this class EGR 352. I really appreciate your hard work and your patience. Even though we have unexpected events like COVID-19 situation, so that we have a one extended spring break, and then after suddenly everything became the remote instruction mode. But I really appreciate your hard work and your dedication. Most of you didn't have any problem. It was kind of, I think, the smooth transition, even though we have this unexpected event. So thank you very much for taking this class, and work hard on this class. If you have any questions or any comments, let me know. I'll be available via email, or if you'd like to set up an individual WebEx session before the final, or even after the final, that would be great. I'm happy to do that, and enjoy your party. So, and by the way, I'll be available during your party time as well. So even during your the final exam, if you have any specific questions, or if you're not clear on any part of the exam, just shoot me an email, that I can reply back to you as soon as possible. All right, thank you, and see you later.